This section is called uh, dynamics, uh, and it's really about Newton's laws of motion. So what we studied in our last week, in our last section, was called kinematics, and that was the study of motion. And in that, we talked about position, velocity, and acceleration. That was most of the progress that we talked about last time was accomplished by Galileo's time. He spent a lot of time quantifying motion, putting numbers to position, putting numbers to velocity, and putting numbers to acceleration, rather than, as the Greeks did, just calling things fast or slow or stationary. He wanted to quantify that, and so he did. And so by the time Newton came along, Galileo died in 1642. Newton was born in 1642. And by the time Newton was a young man, the motion stuff had been worked out. And so Newton was really interested in causes of motion. What causes things to move or to change the way they move? And so this area of physics deals with forces, and it's called dynamics. A force is just a push, a pull, a tug, a yank. It's anything probably you think a force is. So I would argue you've all heard of Newton's laws already, and you know them all individually, probably, or at least two of them, I would say. The first one, and we'll put this in the layperson's perspective, just the ones you probably heard in middle school or from your friends on the playground. An object in motion or at rest remains that way until acted on by a force. That's Newton's first law. Sometimes that's called Galileo's law of inertia. Inertia is sort of, a thing's resistance to changing. When I'm lying on the couch, I have a lot of inertia. It's hard to get me up off the couch. And so things kind of want to keep doing what they're doing. And, and so that's the first law of motion. It says an object will keep doing whatever it's doing, essentially, until it's acted on by a force. The second law, which you may not have heard of, but you might have, is force equals mass times acceleration. So we've already talked about acceleration. And so if something is accelerating, it's because there's a force acting on it. And the acceleration is related to the force that's acting on it by this equation, force equals mass times acceleration. I'll give you a more specific definition of these rules in a little bit. Finally, the third law, which I bet you've heard of, says for every action, there's an equal and opposite reaction. Forces come in pairs. And so this law says if I push on you, you're pushing back on me equally. And this one's, these various laws have been touched on by people in different ways around that time, but the third law is, I think, entirely Newton's, and I think it's really brilliant because it's something that I think you'll see in the coming discussion that is not intuitively obvious. Okay, so first let's just talk a little bit about forces. First of all, a force is a vector, so it has a magnitude and a direction. That's what vectors have. And so a force, if I push you, I push on you with a force of 4 pounds, and I push you to the north, or I push you down, or I push you to the west, or something like that. A force has a magnitude. In that case, it would be the 4 pounds, and a direction, up or north or west or whichever way I was pushing. Forces always have directions associated with them, and they always have a value. That's their magnitude. And so they're a vector through and through. More than one force can act on an object at any time. I'm sitting in a chair right now. Gravity is acting on me. The chair is acting on me. And so they're acting in different directions too. The chair is kind of holding me up, and gravity is pulling me down. So we'll be talking about what we call the net force. The net force is the total effect of all the forces acting, and you kind of have to add them like vectors. Like if I weigh 180 pounds, that means gravity is pulling down on me with 180 pounds. Well, if I'm not moving, then something has to be opposing that, and that's the chair. So the chair is pushing up on me with 180 pounds. If I go back to Newton's laws, um, if I'm by the first law, it says I'll keep doing what I'm doing until I'm acted on by a force. Well, if I'm just sitting here, that means that the net force acting on me is 0 right now. We'll also be concerned with mostly external forces. So internal forces are usually don't affect the motion of an object. You can't push a car from the inside of the car. You can't push a car by leaning on the steering wheel. And so let's switch over to the whiteboard and just talk about a few examples. So I have a cup here. Here's my cup, right? And it's, let's say it's sitting on the table, right? Here's a table here. And so we can start asking, right? Well, what are the forces acting on the cup? Well, if it's anything that's on the surface of the earth, it's being acted on by the force of gravity, right? We can see that the cup is not moving. I'm going to take a drink from it. By the way, you can name these forces anything you want. If it's a weight, you can call it a W for a weight. I usually call it FG for force of gravity, right? There's actually another force acting on this cup because it's not moving. And so if this were the only force, it would be accelerating, according to Newton's second law with F equals ma. But it turns out it's pushing down on the table, and the table is pushing up on it. And so we call this Fn. This is called the normal force. I'll put that back there. Normal is a mathematical term, and it means perpendicular. In this case, to the contact surface. Anytime you put something on a surface, there's a force between the two objects. The eraser is pushing down on the whiteboard's pushing up on the eraser. Those are from Newton's third law. But gravity is pulling down on the eraser, and the table is pushing up on the eraser just enough to balance them. If I push harder down on the eraser, the whiteboard will push harder up. What I'm trying to do really is push the eraser through the table or through the whiteboard, but the forces inside the whiteboard won't let me do that. Now, if I was really strong and pushed hard enough, I could probably push the eraser through the whiteboard, or at least destroy the eraser trying to do that. But I'm not going to push that hard, and I don't think I could anyway. So a couple of things. So we can have more than one forces in it. Often you can see there's a downward force from the weight, there's an upward force from this normal force that we're talking about, and those two cancel each other out. And so I would say the net force is 0, right? And the cup isn't doing anything. I just set the cup there and it just keeps sitting there, right? And so a cup will keep doing what it's doing until acted on by a net external force. And since the net force is 0, it just keeps doing what it's doing. The other thing about these two forces is that these are both external forces. External forces act from outside the object. I didn't say anything in here about the structure of this cup, right? This cup has all kinds of material in it. It's plastic, and it's got ice and water sitting in there. And there are all kinds of chemical bonds that exert forces on each other, but they're all acting inside the cup. And it turns out they all cancel each other out. The only thing that causes things to move is outside forces, external forces. And so when I'm trying to figure out what's happening to some object, I'm always looking at the external forces. not the internal forces. Let me give you another example of that. So imagine I'm driving down the road. I've already drawn a picture of my car. I think it looks like this. It's not red, but might as well be. It does look like that, though. Shorter cab, right? It's raining. And my car, which is, 30-something years old right now, stalls out. So I have a sad face, right? There's the steering wheel. I'm holding the steering wheel. There's my seat. Okay. And so my car is stalled, and I need to get it off the road, right? And so can I get it off the road by just pushing on the steering wheel and pushing it over to the side? I think we all agree that I can't, right? So what has to happen? Right. My wife has to get out and push the car, right? I'm sure you guessed that. Right. So she's applying an external force, right, to push my car forward. But it could be that there's some friction here that's acting on the car so that she can't push hard enough to get it to move, right? So if she's not strong enough by herself, what has to happen? I'll let you think about it for a minute, right? She needs some help, right? And so my daughter has to get out. I don't want to get wet because I've got my nice clothes on. She's also a little bit sad, right? Except my daughter isn't that smart. Can you tell me what she's doing wrong? Right. Her force is opposing my wife's force, right? And so if they push with the same force, F net is F1, if this is in the positive direction, minus F2, because F2 is pointing in the opposite direction. I put a minus sign in front of it. And that's equal to 0, assuming they're pushing with the same magnitude, right? If she's pushing with 30 pounds and she's pushing with 30 pounds. If she was pushing with 35 and she was 30, it would be 30 minus 35 or minus 5 pounds, which means there'd be a 5-pound force that way. Clearly, this is not the right thing to do, right? My daughter needs to come around to this side. I'll just kind of draw her next to my wife, right? And she's pushing, she's got long arms, I guess. She's pushing also, right? And then this is the best way, right? And then we've got F1 and F2 pointing in that direction, right? And then we get F net equals F1 plus F2, right? And then maybe that gets me off the road, right? And I have a smiley face there. You can't see it very well. Right? And so net forces is the vector sum of forces, where I take into account their direction. And external forces are forces acting from outside the object. Those are the keys, right? It's not enough to just say, well, they're both pushing with a 30-pound force, so it's 60 pounds. They have to be pushing in the same direction for those forces to add. If they're acting in opposite directions, then they subtract, right? Okay. So we can come up with a more rigorous version of Newton's laws, right? The first one is an object in motion or at rest remains that way until acted on by a net external force. We would say an object moving with constant velocity will remain that way until acted on by a net external force. Constant velocity can be 0, right? 0 is constant. If it's going with with any uh, with any value of velocity, in other words, the magnitude 10 miles an hour in a straight line, it'll keep doing that until it's acted on by a net external force. The Greeks didn't think this way. They thought that Earth-like objects wanted to be Earth-like and would naturally come to a stop. Galileo showed that objects want to keep rolling, and so this law is sometimes ascribed to him. What he did was he made marbles and rolled them on ramps and showed that the smoother things were polished, the farther they rolled. And that told him that if things were perfect, stuff would roll forever, or that's what he believed. And Newton sort of put words to it, I guess. And so if it's moving, it'll keep going in the same direction at the same speed until it's acted on by a net external force. And so you can feel that if you're sitting in a car. If the car speeds up or slows down, you can feel it, but you can also feel it if the car turns. Remember, velocity is magnitude and direction. If the direction of the car, in order for the direction of a moving object to turn, a force has to act on it. And so, we say an object moving with a constant velocity will remain that way until acted on by a net external force. If the net force is zero, then it'll just keep doing what it's doing. There could be two forces acting on it, just like the car in the rain. It'll keep sitting there if the two forces acting on it cancel each other out. Right? The forces have to be acting from the outside. Internal forces don't cause things to move. The second law looks more or less the same. It just says that the net external force acting on an object is equal to its mass times its acceleration, right? And so, whereas before we just wrote F equals ma, now we've got this little mathematical language here. So F external means external force, and this little sigma here, this Greek letter sigma, means the sum of all. And so what this says is the sum of all external forces equals the mass times the acceleration of the object. So in the case of my mug, the sum of all the external forces is zero. The object is not moving, so it has no acceleration, right? And so that means the sum of all external forces is zero. Gravity is pulling down, the table's pushing up. It's got no net force acting on it. And finally, Newton's third law, which said for every action there's an equal and opposite reaction, is really about forces. And what it says is that forces come in equal and opposite pairs, equal in magnitude and opposite in direction. So for two forces A and B exerting forces, for two objects A and B exerting forces on one another, the force due to A on B is equal to the negative of the force due to B on A. And so let me go back to the mug again. So here's my mug. Right. Right. So the force of gravity on anything is just the Earth pulling down on that thing. The force of gravity on you or the force of gravity on me is the Earth pulling down on you or me, right? It turns out there's a Newton's third law here. This is a little silly. So I just wrote Earth pulling down on mug as a subscript for my F. So it's F sub Earth pulling down on mug, right? That's what the force of gravity is acting. It's just the Earth pulling down on the mug, right? It turns out that there's an equal and opposite. what Newton's third law says is if the earth is pulling down on the mug is pulling up on the earth with an equal and opposite force to this one. So however hard the earth is pulling down on the mug is pulling up on the earth with an equal and opposite force. Now that's not a force that's acting on the mug, that's a force that's acting on the earth. So for any force you can name that's acting on an object, that object is acting on another object with an equal and opposite force. And that's why when I wrote the notes here, I wrote F due to A on B is equal to minus F due to B on A. And you can just switch the nouns. So the force due to the mug on the table is equal to minus the force due to the table on the mug. So we said there's a normal force, right? Right, well, it turns out there has to be, according to Newton's third law, an equal and opposite force for that. That's the mug pushing down on the table. So if all forces come in equal and opposite pairs, the equal and opposite pair for gravity acting on the cup is the cup pulling up on the earth. Because gravity acting on the cup is the earth pulling down on the cup. The cup has to be pulling up on the earth just as hard. We said there was a normal force keeping the cup from going through the table. That's the force of the table pushing up on the mug. That means the mug must be pushing down on the table with an equal and opposite force. Oops. So what does it mean to say the net external force? This is kind of what we've been talking about. If you add up all the external forces acting on an object, this is the net external force. And for the sake of my cup, for the case of my cup, the force of gravity down and the normal force acting up exactly cancel. And so the net external force on my cup is 0. We already know that the net external force on my cup is 0 because we said Newton's second law, the net external force equals the mass times the acceleration here, right? That's Newton's second law. And so since the cup is at rest, its acceleration has to be 0, and that means the net external force has to be 0. If we're sure that there are only two forces acting, in order for them to add up to 0, they have to have equal values and be pushing in opposite directions. And so the normal force and the weight of the cup, in other words, these two forces, this one and that one, have to be equal and opposite because the cup is at rest, right? The acceleration for the mug is equal to 0. So ma mug is equal to 0. And so since the sum of the external forces equals ma mug is equal to 0, that means the net external force is equal to 0. And in order for that to be true, these two forces have to cancel each other out because they're the only two forces acting. That part of it, you just kind of have to take my word for it, but we'll talk about that more as we go. Remember, these other forces aren't acting on the cup. The cup pushing down on the table is not a force on the cup, and the mug pushing down on the table is not a force on the mug, it's a force on the table. And the mug pulling up on the earth is not a force on the mug, it's a force on the earth. And so if we go back here, we can say the net external force is 0, is just the sum of all the external forces, the vector sum of all the external forces. And that's equal to the mass times the acceleration. So in the case where there is a net external force, for example, let's go back to my mug, right? Now I could take this mug and I could say, all right, it's sitting on the table, right? Here it is. I know it's got these two guys. It's got a normal force going this way and a force of gravity going this way. But these two guys add up to 0. So right now the net external force on my cup is 0. Or I could just say this way. But now I'm going to change that because I'm going to give the cup an external force. I'm going to push the cup in this direction. And I'll just call that F, right? Now I can put my cup here. The net force on it is 0, but now I start pushing it and it starts to move, right? When I push it, it accelerates. Now there's friction acting there, and we're going to set that aside for the moment. You can pretend it's a frictionless surface or something like that, right? But now the net external force is just this guy. I could say the sum of the external forces is equal to the normal force minus the force of gravity plus F, where I have to treat these all as vectors. They're all pointing in different directions, right? These two guys cancel each other out because one's pushing down and one's pushing up. This is all that's left, and so the sum of the external forces, or the net external force, is just this guy, right? It's just that guy. And so I can say, look, if there's a net external force of 15 newtons acting on an object that has a mass of 5 kilograms, right, then I can just write down that force is equal to the mass times the acceleration. If that's the net external force, that's equal to the sum of all the external forces. I can figure out what the acceleration is. I can divide both sides by m, and I get this equation. And that says the acceleration is the force divided by the mass. Well, if it's a 15 Newton force in a 5 kilogram object, my cup is not a 5 kilogram object, but we'll just pretend, then the acceleration is 15 divided by 5, or 3 meters per second squared. Notice, by the way, back to this for a second, right? When I say the force is equal to the mass times the acceleration, if I do dimensions on this, the dimensions of force is mass times length over time squared, right? Because acceleration was length over time squared. Remember we were talking about dimensions? And so force is mass times length over time squared. The units for force are, I should say SI units, are kilogram meters over second squared. So those are the units. And we call that a Newton. So a Newton is a kilogram times a meter divided by second squared. That's what a Newton is. And if you come up with your own set of laws about forces, they'll probably name a unit after you as well. So since force equals mass times acceleration, force has has units, that should say units, of kilogram meters per second squared. We call this a Newton. 1 Newton equals kilogram meter per second squared. I'll change that in the written up version, in the online version. And so this is the units, is a Newton. Force has dimensions of mass times acceleration, or mass times length over time squared. Those are the dimensions. Okay, let's see. So, dimensions of units for force. F equals ma means force has units of kilogram meters per second squared. This is called a Newton. And 1 Newton is 1 kilogram meter per second squared. Force has dimensions of mass times acceleration, or mass times length over time squared. Remember, units are what we use to quantify a physical quantity. And these are the physical quantities, right? Mass, length, and time are just the generic names we use for the physical quantities that we want to measure. So what are the equal and opposite pairs? This law, the third law, states that any time an object A exerts a force on another object B, Fa on B, then object B exerts an equal and opposite force on A, which is equal in magnitude and opposite in value, in direction to the first force. And so this is difficult to understand, and this is one of the ones I think that's really attests to Newton's genius, that he sort of figured this out. But if you push on a wall, if you stand on a skateboard, put the skateboard perpendicular to the wall, unless you'll get hurt, but and then push on the wall, and you notice you move away from the wall when you push. Even though you're pushing towards the wall is pushing back on you in a way that makes you move in the opposite direction. And in fact, we even use Newton's third law in a wide variety of places. When you walk, you may not think about it, but when you're walking, you're pushing backward on the ground, and the ground is pushing forward on you. And if you don't think that's true, try walking on something really slippery like ice, and you'll see that what you're trying to do is push backward. And because you can't push backward on the ground on ice, you can't move. It's the same thing with your car. When you drive a car, let me just do some hand drawing here. So here's my car again, right? I'm getting worse and worse as I go, right? If this is the forward direction, so this is me going this way, right? Holding on my steering wheel or something like that, right? When I step on the gas, I'm actually turning my wheel this way. I'm causing the engine to turn the wheel. That's not what makes the car move. What makes the car move is the wheel pushes backward on the ground. So F, wheel on the ground. And according to Newton's law, third law, that means there's an equal and opposite force on the wheel. This is the force, the ground on the wheel, that moves your car forward. And so even though all that is initiated by the engine and by you stepping on the gas, what really happens is you push backward on the ground and the ground pushes forward on the car, or the tire pushes backward on the ground and the ground pushes forward on the tire. And that's what causes the car to move. So all the cars you see going down the highway are being pushed forward by the ground. That's where that force is coming from. I think that's not an obvious statement, and it's the same way you walk. The equal and opposite force comes up in all kinds of places where you might not expect it. When you walk and you move forward, when you're walking, you're pushing backward on the ground, and the ground is pushing forward on you. It happens in lots of cases. So it's back to the writing here. If I push on the wall and the wall pushes back on me with an equal and opposite force, if my windshield hits a moth at 70 miles an hour, the force exerted by the moth on the windshield is equal and opposite to the force exerted by the windshield on the moth. If I throw a potato chip, my hand pushes on the potato chip just as hard as the potato chip pushes on my hand. Those are equal forces in opposite directions. That's really important. I think it's not obvious that those statements are true, but they are. The consequences in this case for the windshield and the moth are very different. Okay. So the last example is my weight is about 180 pounds. This means that the earth is pulling down on me with a force of 180 pounds. By Newton's third law, it means I must also be pulling up on the earth with a force of 180 pounds. That may seem weird to you. So if I jump off not off a building, but off something lower than that so I would survive it, you might think, well, why don't we see the earth coming up? You certainly see me coming down if I jump off a table or something like that, right? And so the consequences for each object has to do with Newton's second law. And so if let's have me standing on a table, right? And I'm going to jump off a table. I have a tiny head for some reason, right? Draw a bigger head there. There we go. All right. You can see my artwork. Here's my artwork. So in the last example here, it says my weight is about 180 pounds. This means the Earth is pulling down on me with a force of 180 pounds. By Newton's third law, I must also be pulling up on the Earth with a force of 180 pounds, right? And so let me just draw this for a second here, right? So if I have a table here, and I'm standing on it, all right, I have to draw a person standing on a table. Well, I'll give myself enough room to have a head. So here's me getting ready to jump off a table, right? Right, and now I jump, and I'm falling, right? Right, like that. And now you know what I look like. Right, here's the ground. While I'm falling, there's really only one force acting on here. It's the force of gravity acting on me. And so this is often called my weight. This is 180 pounds. And so if I were to convert that into newtons, it would be 400 times 2. It's about 900 minus, was it maybe 800? I think we did this already. About 800 newtons, something like that, right? And that would mean that I can figure out what my acceleration is, right? Because the net force acting on me while I'm falling is equal to my mass times my acceleration, right? And so the acceleration is just going to be g. It's just going to be my mass. My mass is about 80 kilograms. And so my acceleration is the force of gravity, which is the net force. It's the only external force that's acting on me, divided by my mass. That's 10 meters per second squared. We'll come back to this. This is the acceleration of gravity, right? We can ask, well, what happens to the Earth, right? Well, remember, the Earth experiences the same external force. Here's the curved Earth below me, which is kind of silly, but let's pretend. I don't mean that it's silly to pretend the Earth is curved. It's just on this scale, the size of the room, the Earth would look flat because we're looking at a teeny tiny portion of it. I don't want to get into that discussion. So, so what we have here is the Earth, and it's getting pulled upward by the same force of gravity, which is 800 newtons. But remember that Newton's second law says that the sum of the forces equals the mass of the object times the acceleration. Well, in this case, the mass is the mass of the Earth, right? And so the acceleration of the Earth is the same 800 newtons, the same force that the Earth pulls down on me, I pull up on the Earth, divided by the mass of the Earth. But the mass of the Earth is not 80 kilograms. It's 6 times 10 to the 24th kilograms. So it's a 6 with 24 zeros after it. So this A is a minuscule number because you're dividing 800 by a bajillion. That's not a bajillion, but anyway, it's a ginormous number. And so the Earth experiences almost no acceleration at all because this 800 Newton force, whereas it causes me to accelerate at 10 meters per second squared, it has almost no effect on the Earth, much the way the moth doesn't have much effect on the windshield of the truck, except to make a little splatter. So even though these forces, the force down on me and the force up on the Earth, are equal and opposite, their effect is very different, right? One of them causes me to accelerate at quite a good rate, 10 meters per second squared. The other hardly moves the Earth at all. Or I should say the Earth's movement is immeasurable. Okay. So now this gives us a chance to talk a little bit about mass and weight. Um, and so mass is kind of a measure of inertia. So let me switch back screens here. Um, it's a measure of resistance that changes to motion. If we look at Newton's second law this way and we rewrite it this way as A equals F over m, you can sort of see that the acceleration is greater if the mass is smaller. If you remember your fraction math, and I'm not asking you to do any right now, I'm just saying look at this quantity. If I exert the same force on a bigger and bigger mass, the acceleration gets smaller and smaller, right? Just as when I had the same force acting on me versus the same force acting on the Earth, the acceleration of the two objects was very different. The acceleration is the force divided by the mass. If we think of how denominators work, the larger the mass, the smaller the acceleration. So when you shake a gift, it gives you an idea how much mass it has by how easily it accelerates when you shake it. If it shakes really easy, then it doesn't have much mass in it. That's what you're testing when you shake a gift. If the same force is applied to a small mass versus a large mass, the smaller mass will have a larger acceleration. So it's difficult to change the motion or shake objects that have large masses. So now let's talk about what we mean by weight. I've just been talking about it like we know what it is. Since Newton's second law says F equals ma, where F is the external force, and all objects near the Earth's surface accelerate downward when released in air at g equals 10 meters per second squared, we already had this discussion in kinematics, then the force of the Earth is exerting on objects must be mass times g, right? When I jumped off that table, my acceleration, like every other object, is 10 meters per second squared. Since my net force is the force of gravity, the force of gravity must just be my mass times that g times 10 meters per second squared. This then is the weight of the object near the Earth's surface. My mass is about 82 kilograms. I said 80. 82 is fine. So my weight is just the force of gravity. It's just mass times gravity is 82 times 9.8 meters per second squared if I want to be precise instead of using 10. And I get about 800 newtons. This translates into about 180 pounds, since 1 pound is 4.45 newtons. And so the weight of any object is equal to the mass of that object times gravity. This is why people will say if you're out in the middle of outer space somewhere away from any object where there's zero gravity, you don't have any weight, but your mass is still whatever it is, in my case 82 kilograms. If you put me out in intergalactic space where there was nothing pulling on me or nothing pulling on me with a significant force, my weight would be zero, but my mass would still be 82 kilograms. If you put me on a really dense object, which has a much higher acceleration of gravity, I would have a much higher weight. I weigh, the moon's gravity is about 1.7 meters per second squared. And so I weigh only about 1/6 of my weight. I would weigh about 30 pounds on the moon, something like that, instead of 180. So here are some questions. A cup sits on the table. Identify two forces acting on the cup. What is the net force acting on the cup? If exactly one force is acting on an object, is it possible for that object to remain at rest? Think about that from Newton's second law. A small running back collides with a much larger defensive lineman. Who experiences the greater force during the collision? A tennis ball of mass 0.2 kilograms is hit by, it shouldn't say but, it should say by a tennis racket which exerts a 40 Newton force on the ball. What's the acceleration of the ball? Assuming that's the only force acting, or that's the net force.